Okay, in today's lecture, we're going to cover the first part of the section 5.3 material on diagonalization of a matrix. And the idea is that for a majority of square matrices, the eigenvalue and eigenvector information about that matrix, let's call our matrix A, can be displayed in a useful factorization of the matrix A, which would have the form A is equal to P times D times P inverse, where D is a diagonal matrix and P is some invertible matrix, so that P inverse exists. So the idea for this section is to make use of that factorization of the matrix A in order to compute powers of K, or powers of A, say something of the form A to the K, pretty quickly for large values of K, which is a fundamental concept in several applications of linear algebra. So when we start, or when you consider applications of linear algebra and these matrices that we've been studying, a common theme or a common problem in applications is to determine A to some large power, say A to the 100th. And in general, to perform those sort of calculations directly would take a lot of time. But the idea is if we can find the eigenvalues and eigenvectors of our matrix, we might be able to express it in this factorization, P, D, P inverse, which will then allow us to find A to large powers much more quickly. So to motivate the idea, let's consider the following example. Let's suppose that we have a matrix D, which is a diagonal matrix. It just has entries on the main diagonal, 2, 3, and zeros elsewhere. And we're asked to find an expression for D to the K power, where K is some integer greater than or equal to 1. So in the problem statement, well, we're given D to the first power. So in order to find D squared, we're going to take D, which was the diagonal matrix, 2, 0, 0, 3, times itself. So multiplying these 2 by 2 matrices, we get a 2 by 2 matrix where our first row, first column is equal to 4. First row, second column is 0. Second row, first column is 0. And second row, second column would be 3 times 3, or 9. So computing D to the third power, we would have the matrix D, which was 2, 0, 0, 3, which we're then multiplying by D squared, which we just found to be 4, 0, 0, 9. So we get a 2 by 2 matrix where our first row, first column entry would be 8. First row, second column is 0. Second row, first column is 0. And second row, second column is 27. So looking at one more power, we see a pattern emerge if we haven't already noticed it. So to get D to the fourth power, we would take D, which was 2, 0, 0, 3, and multiply by D cubed, which we just found to be 8, 0, 0, 27. So we get the matrix whose first row, first column is 16, 0, 0, and 3 times 27 is 81. So we start to see a pattern emerging here. If we don't see the pattern directly from these numbers, we could think about rewriting these products as follows. So for D squared, my first entry was 2 squared, and then 0, 0, and 9, which is 3 squared. For D cubed, our first row was 8, or 2 cubed, 0, and the second row was 0, 27, which is 3 cubed. And then for D to the fourth, our first row was 16, or 2 to the fourth, 0, And the second row is 0 and 81, which is 3 to the 4th power. So in general, d to the kth power would be the diagonal matrix, where our diagonal entries are 2 to the k and 3 to the k for any k greater than or equal to 1. So for diagonal matrices, finding large powers is quite easy. You just take that power of the entry on your diagonals. So let's consider the problem of interest for this section. Let's suppose that a matrix A can be rewritten as the following factorization: P times D times P inverse for some invertible matrix P in some diagonal matrix D. So I claim that A to the K can be easily computed, as we'll see in the following example. So here we're told to find a formula for A to the kth power if we are given that A can be written as the product of PD and P inverse, where P and D are the 2x2 matrices given here. So my first step in this problem might be to find P inverse. I have P and D, but I need to know what P inverse is. So here, P inverse, using the formula for the inverse of a 2x2 matrix, is given by 1 over the determinant of P, which is 10 minus 9, or 1. So we have 1 over 1, or simply 1 out in front, times the 2x2 matrix that we get by interchanging our diagonal entries and changing the sign of the off-diagonal entries. So P inverse is the matrix 5, 3, 3, 2. So now, if I'm going to start computing powers of A, I'm going to be making use of the associativity of matrix multiplication. So let me say by associativity of matrix multiplication, if I'm interested in finding A squared, well, A is equal to P D P inverse, so I'm multiplying that quantity by itself. But using the associativity of matrix multiplication, I can rewrite this as P times D times P inverse times P, and then times D times P inverse. If I group these middle two terms together, I have now P inverse times P, which of course is the identity matrix. So now we have A squared is equal to P times D times the identity matrix, which we're then multiplying by D times P inverse. So remember, the identity matrix times any matrix, namely dP inverse, would just give us dP inverse. So now, for the middle of this product, I'm multiplying D by itself. So I have P D squared P inverse. So if I want to find A squared, I would take the product of P times D squared, and we know that D squared would be easy to calculate since D is diagonal, and then multiply by P inverse. So explicitly, I could write this out as 2, -3, -3, 5, times D squared, which would be the matrix which has the square of the diagonals since D was a diagonal matrix, times P inverse. 5, 3, 3, 2. So now if we're looking for A cubed, well, we're taking A, which is P times D times P inverse times A squared, which we just found was P times D squared times P inverse. So recall this formula for A squared that we found here. So again, using the associativity of matrix multiplication, I can think of this as P times D times P inverse times P, and then times D squared times P inverse. So again, this middle part of our product, P inverse times P, is simply the identity matrix, which acts as a 1 for matrix multiplication. So I'm left with P times D times the identity matrix would just be PD, and then we're multiplying by D squared times P inverse. So this middle part of our product where we have D times D squared becomes D cubed. So I have P D cubed P inverse. Or if I write this out explicitly, P was the matrix 2, -3, -3, 5, times D cubed, which would be the diagonal matrix, where the diagonal entries are 2 cubed and 3 cubed, times P inverse, which was 5, 3, 3, 2. So for A squared, we had, it was equal to P D squared P inverse, and for A cubed, we found that we could take P D cubed times P inverse. And we know that this middle part of our product, D raised to some power, is the matrix we get by simply taking the diagonal entries of the diagonal matrix D raised to that same power. So in general, we can say A to the K power could be expressed as P times D to the K power times P inverse. Or writing this out explicitly, we have the matrix P, which was 2, -3, -3, 5, times D to the K power, so our entries would be 2 to the K and 3 to the K on the diagonal and zeros elsewhere. And then P inverse, which is 5, 3, 3, 2. So let's see what we get when we multiply these three 2x2 matrices. So you could first take the product of these first two and then multiply that product on the right by the following matrix. And you end up with the matrix 10 times 2 to the K power minus 9 times 3 to the K power. And in that first row, we would also have 6 times 2 to the K minus 6 times 3 to the K. And for our second row, our first column is -15 times 2 to the K minus 9 times 3 to the K. And second row, second column gives us -9 times 2 to the K minus 6 times 3 to the K. So ran out of room here at the end, but you can verify this product if you take the product of those three matrices. So this example is illustrating if we can find a factorization of the square matrix A, which has the form P times D times P inverse, where D is a diagonal matrix, then we can use this same sort of process to easily evaluate A to higher powers. So the question is, well, can every matrix A be written in this sort of factorization? And the answer is no, not always. So then, of course, the next question is, well, when can you write a matrix in that form? So let's consider that question here. We would say that a square matrix A is diagonalizable if the matrix A is similar to a diagonal matrix. So that is, if A can be expressed in the factorization P D P inverse for some invertible matrix P in some diagonal matrix D. So the following theorem will give us a characterization of diagonalizable matrices, and it will tell us how to construct such a factorization. So the question is, well, when is a matrix A diagonalizable, and how do we find that factorization P D P inverse? So the following result, theorem 5.5 from your text, is called the Diagonalization Theorem, which says that a square matrix A, in particular n by n matrix, is diagonalizable if and only if A has n linearly independent eigenvectors. So the dimension, let's say the number of rows or columns of our matrix, this matrix must have that same number of linearly independent eigenvectors. And in this case, the matrix A would have a factorization P D P inverse, with D being a diagonal matrix, if and only if the columns of P are n linearly independent eigenvectors of A. So this says, well, to form the matrix P, we would take the n linearly independent eigenvectors of our matrix and make them the columns of a matrix, and that would be P. And then the diagonal entries of the diagonal matrix D would be the eigenvalues of the matrix A that correspond respectively to the eigenvectors in P. So for instance, the first eigenvalue, say the 1, 1 entry of our diagonal matrix D would correspond to the eigenvector that is the first column of the matrix P. So what this theorem says, stating this another way, is that a matrix A is diagonalizable if and only if there are enough eigenvectors to form a basis of Rn. And in this case, we would call such a basis an eigenvector basis of Rn. So let's consider one application of this theorem. So this is the more uncommon application of this theorem. Let's suppose that for a matrix A, we have found a factorization A, which is of the form P D P inverse, shown here. So in this problem, this is our matrix A. Here we have P, D, and P inverse. And we're told to use the diagonalization theorem to find the eigenvalues of A and a basis for each eigenspace. So the eigenvalues of our matrix A should be the entries of the diagonal matrix D. That follows directly from the diagonalization theorem. So the eigenvalues of A are the diagonal entries, which were 5 and 4. And we see that 5 was an eigenvalue of multiplicity 2. It's repeated more than once. Now, to find a basis for each of these eigenspaces, we need to look at the columns of our matrix P. By the diagonalization theorem, these columns of P should be a set of linearly independent eigenvectors corresponding to the eigenvalues in D. For the eigenvalue, let's say lambda 1 equals to 5, a basis for the eigenspace is, let me call it B1, and it would be the set of the first two vectors from P. Now, why the first two? Well, 5 was an eigenvalue of multiplicity 2. It was listed in both the first and the second column of D. So the vectors in the first and second column of P would be eigenvectors. And we can see by inspection that they are linearly independent. One is not a scalar multiple of the other. Therefore, they form a basis for our eigenspace. So our first vector would be -2, 0, 1. And our second vector for this basis would be 0, 1, 0. Now for the eigenvalue lambda 2 equals to 4, a basis for the eigenspace is, let me call it B2, which would consist of the single vector, which is the third column of P, -1, 2, 0. So here, since the third column or the third diagonal entry of D was our eigenvalue 4, this third column vector of P must be a corresponding eigenvector. And every other eigenvector would be a scalar multiple of this one. So it forms a basis of dimension 1, or this eigenspace is one-dimensional with this basis vector. So now the more practical application of the diagonalization theorem is in finding a diagonalization of a given matrix. So let's pose the following question. For the following 2 by 2 matrix A, let's diagonalize it if it is possible. So the diagonalization theorem says we need to find the eigenvalues and eigenvectors of our matrix A in order to find this factorization. So to find the eigenvalues of this matrix, recall from our last section, we would consider the determinant of our matrix minus lambda times the identity. So that is where we're subtracting lambda from the diagonals. And this would give us 2 minus lambda times 1 minus lambda minus 12. So that is our characteristic polynomial. And we're looking for the roots of that polynomial. So expanding, we have lambda squared minus 3 lambda plus 2 minus 12 leaves us with -10 equals 0. And then this factors as lambda plus 2 times lambda minus 5 is 0. So our eigenvalues are -2 and 5. So we've got our eigenvalues, and we need to find a set of linearly independent eigenvectors. So the diagonalization theorem says as long as we have 2 linearly independent eigenvectors for this matrix, since it's 2 by 2, then it is diagonalizable. So let's consider finding eigenvalues for these vectors. So here, if we look at our first eigenvalue, lambda 1 equals -2, then recall to find an eigenvector, we're looking at the matrix A minus lambda I. So if lambda is -2, minus lambda I would be plus 2i times some vector, let's call it x1, and we're looking for solutions of this homogeneous system, which are non-trivial. Those are non-zero vectors. So expressing that equation or system as an augmented matrix, well, we're adding 2 to the diagonal entries of A for our coefficient matrix, or subtracting lambda, which was -2. So we have the matrix 4, 3, 4, 3, which we're then augmenting with the 0 vector. So it's clear that our rows and columns are linearly dependent, so there are non-trivial solutions of this equation. And it's clear by row reducing that this is row equivalent to the matrix 1, 3/4, 0, 0, 0, 0. So by taking the second row minus the first and dividing the first row by 4. We have x2 as a free variable, and then using the first row of this augmented matrix, we would see that our solutions are of the form x1 is equal to the free variable x2 times negative 3/4, 1. Or if we don't like that fraction in our first entry, we can think about this as the free variable x2 times negative 3, 4, because any scalar multiple of negative 3, 4 would be a scalar multiple of negative 3/4, 1. So an eigenvector, if we need to choose one particular eigenvector, I could take, say, x2 as being equal to 1 or negative 1. So an eigenvector would be, let's call it v1, which might be, say, 3, negative 4, if I choose x2, my free variable, as negative 1. But you can choose any non-zero value for x2, and you'll get another eigenvector. Now for our second eigenvalue, lambda 2 equals to 5. To find an eigenvector, we're looking at a minus lambda, which was 5, times I, times some vector x2 is equal to the 0 vector. So expressing that as an augmented matrix, subtracting 5 from the diagonal entries of A, we have negative 3, 3, and 4, negative 4, which we're augmenting with the 0 vector. So it's clear that this is row equivalent to the matrix 1, negative 1, 0, 0, 0, 0. So again, x2 is a free variable, and the vector x2 could be written as x2 times 1, 1. From the first row of this matrix, we see the components of our vector x1 and x2 have to be equal to one another. So making one specific choice for the free variable x2, we can get an eigenvector. Which I'll call v2, which we could take as 1, 1 if we choose x2 as being equal to 1. Moreover, these eigenvectors that we've chosen, v1 and v2, are bases for the corresponding eigenspaces. So any eigenvector has to be a scalar multiple of these eigenvectors, so they form a basis. And we can see by inspection that v1 and v2 are linearly independent, since they are not scalar multiples of one another. So we'll say clearly these vectors v1 and v2 are linearly independent. So to form our diagonalization of A, we're going to take the matrix P as the matrix which has these vectors as its columns. So that is 3, negative 4, and 1, 1. And D will be the diagonal matrix whose entries are the corresponding eigenvalues, which were negative 2 and 5. Where we list negative 2 first because the first column of P was the eigenvector corresponding to negative 2. So we have to make sure that our columns coincide here. So this would be our matrix P and D to form the factorization of A as P times D times P inverse. And you can verify that this is a valid factorization of A. So if you compute A times P and show that that's equal to P times D, you've shown that A can be written in this form. So as a double check, you can always calculate A times P and P times D, and as long as you get the same expression, you verified that A is P D times P inverse.